Hello, welcome to our second video on parametric equations. In this video, we're again going to take a look at how to construct parametric equations for a curve if you have a description of the curve. This will be a higher level application than what we saw in the previous video where we looked at equations for a line, but this also illustrates several important techniques that will be important in the future and when we work with polar equations. The curve that we describe is going to be called an epicycloid. It's very similar to the cycloid, so let's review the cycloid first. There's a very good discussion of the cycloid in the textbook. The cycloid is a curve traced by a fixed point on a circle, usually called a point P, that starts down here on a line. The circle rolls along the line, and the point P is traced out as the circle moves. Here are a couple of videos showing how a cycloid is traced by the path of a fixed point P on a moving circle. As the circle moves, the path of the point P is traced in red. When constructing parametric equations for a curve, the choice of parameter is often very important. When they derived the parametric equation for the cycloid in the textbook, they used as parameter the angle phi through which the circle is rolled. The goal is to find equations for the coordinates of the point P, and those equations were expressed as a function of the angle phi through which the circle has rolled. They came up with these equations, x given by a times phi minus a sine phi, and y equals a times 1 minus cosine phi. And these express the coordinates of the point P at any given time. Now, the work in constructing these equations consisted of two parts. The first part was to find the coordinates of the center of the circle once it has moved through a certain angle. So in the derivations of the cycloid equations, they first said that if the circle is rolled through this angle phi, then the coordinates of the center were given by that expression. The a phi represents or is equal to the length of this arc through which the circle is rolled, which turns out to be the same as the length of this horizontal piece. And then, of course, the circle, if it has radius a, the center stays at level a, hence the y-coordinate stays at a all through the rolling. Okay. So once this center was determined, we then looked at how the point P was displaced from the center, again for the various positions through which phi is taking as the circle rolls through this angle phi. So the next step was to find out for this point P what was the horizontal displacement, that is how far was P displaced horizontally, either left or right, and then secondly, what was the vertical displacement, so how far up or down from the center position was this point P. And we found that then x phi, y phi could be found by noting, okay, we know where the center is, that's there, and then adding the displacement from the center. So here was the center, a phi comma a, and the displacement, we saw minus a phi horizontally and minus a cosine phi vertically. And when you put those two together, you then have coordinates for the point P. We're going to use a similar approach when we look at deriving the parametric equations for an epicycloid. Now, an epicycloid is the path traced out by a point P on a circle as it rolls along the outside of another circle. So here's a figure of what we're going to be looking at here. So here's the starting point. This is the rolling circle on the outside. We refer to this circle as the fixed circle, and the rolling circle moves along the outside of the fixed circle. We're going to call the radius of the fixed circle A, and the radius of the rolling circle will be B. So as this fixed circle rolls along the outside, this point P traces a curve. It turns out to look something like this. We're going to find out what the equations are for the position of the point P, what are the x and y coordinates in terms of an appropriate parameter. Here's a video of how an epicycloid is generated. We can see that smaller circle in black going along the outside of the larger circle, the blue one, And that red point P, there was a red pen attached to the point P, traces the epicycloid as you see there. Now, depending on the relative radii of the inner and outer circles, you may have different looks to the epicycloid. Here's another example. We've already done some drawing here. So here we have, here we see a slightly larger circle relative to the big circle. And we can see that it doesn't really come out even and rolling around the big circle. So here the epicycloid takes on a more interesting look, many different lobes, etc. Let this run a little bit and see where it ends up. Here's the start. So here it rolls around the circle. There's kind of one revolution. Then the point P hits the fixed circle again here. Doesn't quite come out even, so it continues around. Point P hits the fixed circle there. And so this is another way that the epicycloid might look, again, depending on the relative sizes of the inner and outer radii. So we'll derive the equation for the epicycloid in a manner similar to that of the cycloid. We'll first find the position of the center of the rolling circle. Then we'll find the horizontal and vertical displacement of P from this center. We're going to use two elementary facts from trigonometry. And the first is this: in a circle of radius r, the length s of the arc subtended by a central angle of measure alpha is equal to s alpha. Now here's what that looks like geometrically. So in this case, suppose we have an angle alpha here on a circle of radius r. We'd like to know how long is this arc that is, as they say, subtended by this angle. We can do this by a simple ratio. Now, a full circle subtends an angle of 2 pi. That might look something like this. Here's the full circle, measure 2 pi. And so that red arc is going to be fraction alpha over 2 pi of the full circle. And of course, the full circumference has value 2 pi r. So we can set up a simple ratio to see the length of s. Particularly our ratio then says s is what fraction of the whole radius? Well, it's the fraction alpha over 2 pi. And so we can solve for s. The 2 pi's cancel. We're left with s equals r alpha. So again, it's just a matter of s is what fraction of a whole circumference. Well, that fraction is the same as what fraction the angle alpha is of a full rotation of 2 pi. Then it's just easy algebra. The second fact we'll need involves looking at displacement from the center. So suppose we have a circle of radius r, and let a equal r0 and b be some second point in the circle with angle alpha OB equal beta. The circle, of course, centered at the origin. And we claim that b then has coordinates r cosine theta, r sine theta, and so from the center of the circle, the horizontal displacement is r cosine beta, the vertical displacement is r sine beta. So there's what our picture looks like. And of course, if you remember your trigonometry well, this is really nothing more than the circle definitions of the trigonometric functions. So in particular, we know that if we take a look at an angle beta here, the even right triangle trigonometry here shows us how these coordinates are given by just simple trigonometric relationships. If the circle has radius 1 and so r equals 1, then these coordinates are just cosine beta, sine beta, which gets you back to the unit circle definition of the trig functions. So this is how we're going to measure the horizontal displacement and the vertical displacement of a point like B from the center of a circle. The horizontal displacement will be r times the cosine of whatever angle we have here, and similar for the vertical displacement. Now notice that we're talking displacement, not distance. Displacement to the left is considered negative, so in this case, the r cosine beta would be negative because the displacement of B from the center O is to the left. So in constructing the parametric equations for the epicycloid, we're going to work in the xy plane. The origin will be at the center O of the fixed circle. which is the large circle in this picture. We're going to take as our parameter here the angle theta determined by the positive x-axis. It's right here. O, and then the ray through the center of the rolling circle. So this angle theta is going to be our parameter. So if the circle has rolled, so this angle from the center BO along the x-axis makes angle theta, then what are the coordinates of the point P, which would now be up in that position? Now, because the little circle has radius B and the fixed circle has radius A, it's pretty clear that this center always rolls along a circle of radius A plus B centered at the origin. In other words, the center B of the rolling circle stays on that dotted circle we see there. So we'd like to know what are the coordinates of B to start, what are the coordinates of the center of that circle. And because we know this central angle, which we're calling theta once again, parameter is that angle theta, as we saw earlier, the displacement, if we know the central angle and the radius, the displacement from the center, the horizontal displacement is A plus B cosine theta, and the vertical displacement A plus B sine theta. And so that gives us these coordinates for the center in terms of the angle theta that kind of measures how far the rolling circle is moved along the fixed circle. Next, we calculate the displacement of the point P from the center of the rolling circle. Again, we do this in terms of theta. Now, before we do that, we have to do a little groundwork. Let's let T be the point of tangency, the point at which the rolling circle is tangent to the fixed circle. And because the circle rolls without slipping, the arc traced in green along the fixed circle is going to be the same as the arc illustrated in red along the rolling circle. Okay. That means the arc suspended by theta on the fixed circle has the same arc length as the arc subtended by phi on the rolling circle. Now, as we saw earlier, we can find expressions for these two arcs, the lengths of these two arcs, and those are given by, well, the green arc, subtended by the angle theta in a circle radius r, that has length a theta. The red arc has length b phi, because we're in a circle of radius b and the subtended angle is phi. Again, those have to be equal if the rolling circle moves without slipping. And so from that equation, the fact that those two things are equal, we can solve for phi and find that angle phi has expression phi equals b over a times theta. Now finally in the figure, we're going to add a horizontal line also right here from the point T. So we see that here. And of course, once we add that horizontal segment, we can see that this angle between segment RB and the radial line out here is given by theta. And that's because this angle is theta, and because we have a transversal cutting horizontal lines here, RS is horizontal on the x-axis, that angle RBT must also be theta. So we now know the angle we've indicated in red here. We know this angle TBP because of the relationship between the lengths of the red arc and the green arc. So we now have everything we need to know to calculate the displacement of P from the center of the rolling circle. Remember, we know what that center is. We found that a little earlier. As seen in earlier discussions, this displacement can be found once we know the angle from the horizontal BS out to the segment BP. For a better view, let's zoom in on this rolling circle. Now we're going to measure this angle by actually going once around the small, that is the rolling circle. This seems strange, but the geometry of the picture makes this the easiest way to calculate the angle. So instead of calculating the angle by just going from the horizontal segment up to here. We're actually going to go around the circle once and then finish back up at the ray BP. So why is that angle easier? Well, we know three angles that lead up to that. And these angles are, first of all, the straight angle, SBR, that has measure pi because it's a 180-degree angle. So as we go from BS to BR through an angle, that angle is pi as indicated on the figure. Next, we have the angle RBT. As we saw earlier, that angle has measure theta. And then finally, to complete the trip around to the segment BP, we have the angle TBP, which we calculated earlier as AB over theta. So by adding these three angles together, we've actually measured again this angle from the horizontal around once and then back to the segment BP. So thus we're going to say angle SBP is, again with this going once around the circle before we get back to it, pi plus theta plus A over B times theta, which reduces to the expression we see right here. Now that we know that angle, we can figure out the horizontal and vertical displacement and finally get our position for the point P. So for the horizontal displacement measured in red and the vertical displacement measured in blue from the center, we have the following. The horizontal displacement, as we saw earlier, is just given by the radius of the circle times the angle needed to get up to that point. That angle was SBP. So that gives us this expression, the horizontal displacement, which is in red, given by BP times the angle. The angle was given by pi plus A plus B over B times theta. And easy trigonometric identity is that if you add pi to an angle, you just negate the trig function. This is because you're going halfway around the circle. So this all settles down to minus B cosine A plus B over B theta. For the vertical displacement, very similar. The vertical displacement is given by B times the sine of the angle. And again, that sine is pi plus A plus B over B theta right here. And again, you go halfway around the circle. That is the add pi to an angle, and you just negate the trig function. Okay. So there is the vertical displacement. And so once we know the position of the center and the vertical displacement, we can come up with our parametric equations. So recall that we found that the center of the circle in terms of theta was given by A plus B cosine theta, A plus B sine theta. And so the position of the point P is given like this. We have the coordinates of the center B, that's given right above here, and we have the displacement of P from B. And so we just have to add the coordinates of the center, the horizontal and vertical displacement, and they come together into one system like this. And so here is our x coordinate for point P, and here is our y coordinate. So this leads to the equations. X of theta equals A plus B cosine theta minus B cosine of the quantity A plus B over B times theta. And for y of theta, A plus B sine theta minus B sine of A plus B over B times theta. So these are parametric equations for the epicycloid, the path traced by a point P on a circle of radius B as it rolls along the outside of a circle of radius A. Now, it'd be good practice with your polar calculator to pick some values for A and B, say A equals 3, B equals 1, something like that, and then try plotting these on your calculator. Do you really get a picture that looks like an epicycloid? Change the values A and B if you want to see the different ways epicycloids might look. So what did we learn in this video? In constructing parametric equations for a curve, you really want to give some thought to how you will place the xy plane in your work, where's the origin, etc., where are the axes going to go, and then what will you use for your variable in your equations? That is, what will the parameter be for your parametric equations? It's often difficult just to look at a curve and instantly discern the equations for x and y, whatever the parameter. So often this is more easily done in steps. And in deriving the equations for the cycloid and the epicycloid, we saw these steps consisted of two things. One, first finding the center of a circle, and then two, find the displacement of the desired point from the center. We had valuable trigonometric ideas involved in both those pieces. And in fact, elementary trigonometry is often very useful in constructing parametric equations. And two of the very important and recurring yet basic ideas are the formula for the length of a circular arc subtended by a central angle, and also ideas that allow us to express the coordinates of points in a circle in terms of the sine and cosine. This, of course, just gets back to the unit circle definitions of the trig functions, which are always very important and show up in many, many applications. But both these ideas are very important when we study polar equations also, and so we'll be seeing these come up again in later sections. So thanks for listening to this. We'll see you in the next video. Bye.